Welcome to the first video on the channel, which relates to the fascinating realm of the Earth sciences. Today we delve into a captivating topic that will transport us back in time as we uncover the enigma of Earth's ancient supercontinent, Pangaea. We will explore the methods employed by scientists to ascertain the existence and timeline of Pangaea. But before we dive into the evidence, let's take a moment to understand the intriguing background and development of the theory. The story of Pangaea begins with this guy, Alfred Wegener, German climatologist, geologist, geophysicist, meteorologist, polar researcher, and all-round bright spark. In the early 20th century, Wegener proposed the revolutionary idea of continental drift. He noticed that the continents seemed to fit together, much like the pieces of a grand jigsaw puzzle. The coastlines of South America and Africa, for instance, appeared to align seamlessly. This observation led Wegener to speculate that the continents were once connected. However, the man delving into deep time was ahead of his time. Faced with considerable skepticism and opposition from the scientific community in 1912, his ideas challenged the prevailing belief in static continents and a fixed Earth. Moreover, he lacked a comprehensive mechanism to explain how the continents could move across the Earth's surface. It wasn't until several decades later, in the 1960s, that the theory of plate tectonics emerged, providing a breakthrough in our understanding of Earth's dynamic nature. Scientists realized that the Earth's lithosphere consists of large rigid plates that float atop the underlying semi-fluid asthenosphere. These tectonic plates interact at their boundaries, creating geological features such as mountains, trenches, and volcanoes. The concept of plate tectonics provided the missing piece of the puzzle for Wegener's theory of continental drift. It explained how the continents could move over vast periods of time. The movements of the tectonic plates pushed, pulled, and collided with each other, causing the continents to drift apart or come together. With the acceptance of plate tectonics, the theory of Pangaea gained significant credibility. Scientists realized that Wegener's intuition was correct. Our continents were once part of a single, massive supercontinent called Pangaea. The name Pangaea itself comes from the Greek words pan, meaning all, and gaea, meaning earth. To piece together the puzzle of Pangaea, scientists embarked on extensive research, utilizing various methods. Researchers delved further by studying rock formations and fossils found on separate continents. They have unearthed astonishing similarities in rock layers and fossilized flora and fauna on land masses that are now geographically distant. For instance, matching rock layers and fossil records have been discovered on the eastern coast of South America and the western coast of Africa. Such findings strongly indicate a past connection between these regions. Another method used by scientists is known by the term paleomagnetism. Paleomagnetism is a remarkable field of study that helps us peer into Earth's magnetic history, offering valuable clues to the movement of continents and the existence of Pangaea. To understand this fascinating occurrence, we must first grasp the concept of Earth's magnetic field. As our planet behaves like a giant magnet, it generates a magnetic field that surrounds it. The source of this magnetic field lies deep within the Earth's outer core, where the churning of molten iron generates electrical currents. These electric currents create a magnetic field that extends far beyond the Earth's surface. As magma and lava cool and solidify into rocks, their iron-rich minerals align themselves with the Earth's magnetic field. These minerals act like tiny magnetic compasses, preserving the magnetic orientation of the Earth at the time of their formation. The beauty of paleomagnetism lies in its ability to time travel. Geologists can analyse the preserved magnetic orientations in rocks and minerals and compare them to the present day magnetic field. By doing so, they can discern the positions of the continents in the past. Let's illustrate this with a fascinating example. Imagine we find a rock formation that records a particular magnetic orientation. If we can determine the age of that rock, more on that later, we can then use paleomagnetic data to estimate its original location on Earth's surface when it formed. When scientists studied rocks from various continents, they made a jaw-dropping discovery: identical magnetic orientations in rocks found on continents now separated by vast oceans. This finding was a eureka moment. It corroborated the theory of Pangea. For instance, rocks from the east coast of South America showed a magnetic orientation that aligned perfectly with the rocks from the west coast of Africa. Such a striking resemblance strongly suggests that these two continents were once joined together. The discovery of this apparent polar wandering path provided compelling evidence for continental drift. By tracing the ancient positions of continents using paleomagnetic data, scientists could reconstruct the past positions of continents and hypothesize their former supercontinent configuration, Pangaea. Now that we have the evidence, let's delve into the timeline of Pangaea's existence. Scientists have employed a technique called radiometric dating to determine the ages of rocks and minerals. By analysing the decay of radioactive isotopes, they can calculate the ages of these materials. Radioactive isotopes? What are they, and how do they relate to determining the ages of rocks and minerals, I hear you cry. Radioactive isotopes play a pivotal role in the study of Earth's history, including the timeline of Pangaea's existence. To grasp their significance, let's first understand what isotopes are. Atoms of the same element can have different numbers of neutrons, resulting in variations known as isotopes. Some isotopes are stable, while others are unstable or radioactive. Radioactive isotopes undergo a process called radioactive decay, wherein the nucleus of the atom spontaneously breaks down, emitting particles or energy. This decay occurs at a predictable rate, expressed as a half-life, the time it takes for half of the radioactive isotopes in a sample to decay. Geologists employ various isotopic systems depending on the nature of the rock or mineral being studied. The information obtained from these isotopic dating methods provides crucial insights into the age and chronology of Earth's geological events. In the context of Pangaea, scientists have applied radiometric dating techniques to various rocks and minerals found on different continents. By dating the formation of these rocks, they have been able to piece together the timeline of Pangaea's existence, from its initial formation to its eventual breakup. Using this method, they have determined that Pangaea began to form approximately 335 million years ago and completed its breakup around 175 million years ago. So let's summarise. Matching rock layers and fossils found on different continents provided crucial clues. The study of paleomagnetism revealed identical magnetic signatures in rocks across separate landmasses. Radiometric dating techniques allowed scientists to estimate when Pangaea began to form and when it ultimately broke apart. Through these meticulous methods, scientists discovered compelling evidence that confirmed the existence and timeline of Pangaea. We continue to refine our understanding of Pangea and its influence on the distribution of flora, fauna, and geological features we see today. And there you have it. Curiosity satisfied. Oi, you be careful you don't get yourself killed. If you have come across a fact that made you go, how do they know that? Leave a comment in the comment section. We will endeavour to provide you an answer. If you enjoyed or got value from the video, please smash that like button and subscribe to the channel to ensure you don't miss out on upcoming videos. Until then, maintain curiosity, stay wholesome, and we'll see you in the next.